All right, you guys, Chapter 10, Lesson 3, Solving Problems with Inequalities. Okay, we're going to use what we just did in the last lesson, set up some word problems and solve them. So there's all that's new here is thinking through a situation and applying the appropriate inequalities. So let's do an example. Molly set her car's trip odometer at 0 at the start of her trip home. When the odometer showed that she had driven 16 miles, a highway sign showed her that she was still more than 25 miles from home. What is the minimum total distance to the nearest mile that she will have traveled when she arrives home? What's the minimum total distance to the nearest mile? Okay. Let's think this through. What are we looking for? The minimum total distance. Okay, so that's what we're looking for. Now let's pick a variable. Let's say D is the distance traveled. Because we're looking for how far did she go. Okay, so D is the distance in miles. Now, D minus 16 is the distance from that sign to her house. Okay, so we've got two different quantities here. We've got the distance that she's traveled and the distance that she is from her house. Because remember how this thing's working. She's out here somewhere and she's going home. Okay, so she pushed a button on the odometer and it's 0 here, and so then she noticed it's 16. When she had driven 16 miles, there's a sign and it says 25 more to go. Okay, so how far will she have gone when she gets home? Well, let's see. It's the minimum distance. She could go more. She could veer off and get a Starbucks or come over here and get a hamburger or whatever. So the question is, what's the minimum distance? So we picked D as the total, and then we said the distance from her house, from her house to the sign is D minus the 16. Let's make sure that makes sense. The whole thing is D, but she already went 16. So from the sign to her house is the total minus 16. Now we know it's going to be 25, but it could be more. So we're saying D minus 16. Then we're going to represent the situation with an inequality. We're going to say that the distance from the sign to her house is more than 25 miles. Okay, so now we can solve it. So the distance that she goes has to be more than 41 miles. So notice it can't be equal to 41 miles. So the smallest number that she can go is 42 miles. Okay, that's it. We solved it. Let's do another one. Before we do another one, though, make sure you understand, sometimes they'll say is at least, or is no less than, or is at most, or is no more than. You've got to learn how to translate these phrases. If you say is at least, what you mean is that it's bigger than or equal to 70, or something. I'll just pick 70. It's bigger than or equal to something. If you say is no less than, you mean it could be bigger or it could be equal to. If you say is at most, what you mean is it's less than or equal to. And if you say is no more than, you mean the same thing. So you've got to get these words down. Think them through to see if they actually make sense to you. Okay, another example. Example number 2. Mike wants to rent a car for his vacation. The car costs $125 for the week. $125 for the week and 15 cents a mile. He doesn't want to spend more than $200. How far to the nearest mile can Mike travel if he wants to spend at most $200? Now, at most. So let's just think it through. Can it be less than $200? Yes. Can it be equal to $200? Yes. So the money has to be less than or equal to $200. That's what at most means. Okay, what's the problem asking for? The number of miles that he can go and still be at 200 or less. Okay, so let's give that a variable. Let's call it m is equal to the number of miles. Okay, and now how much does the thing actually cost? Well, the thing actually costs $125 no matter what, plus 15 cents for every mile. Now let's make an equation. The total cost has to be less than or equal to $200. Let's solve it for the miles. So we have 0.15m is less than or equal to 75 divided by 15 cents. The miles can go have to be less than or equal to 500. So what is the most number of miles to the nearest mile? He can go 500 miles on his trip. He can go up to and including 500 miles. Okay, let's do one more example. Example number 3. This one's slightly more complicated. The width of a rectangular computer screen is 20 centimeters less than twice the length. Okay, so we have the length here, the length of a computer screen, and then the width is 20 less than twice the length, and the perimeter is at least 53 centimeters. What's the smallest the screen could be if each dimension is an integer? Now let's translate at least. So we know, can it be bigger than 53? Yes. Can it be equal to 53? Yes. At least 53. So the perimeter is greater than or equal to 53. Now we already picked a variable here. The length of the screen is L. The width of the screen is 2L minus 20. Now, the perimeter has to be bigger than or equal to 53. So let's make us an equation. So since the length is counted twice in a perimeter, we're going to have 2L plus these two sides, which is 2 times 2L minus 20. And that's the perimeter. It has to be bigger than or equal to 53. Let's solve. 2L plus 4L minus 40 is greater than or equal to 53. 6L minus 40 is greater than or equal to 53. Add 40 to both sides to solve. 6L is greater than or equal to 93. Divide by L. L is going to be bigger than or equal to 15.5 centimeters. Now the problem is, it said it has to be integer dimensions. So what's the next largest integer? It's got to be bigger than or equal to this. 16 centimeters. So the smallest dimension for its length would be 16, and then the width would be 12. 32 times 16, 32. 32 minus 20 is 12. So the smallest the screen can be is 16 by 12. Okay, that's it. You guys work the problems. Let me know if you have any questions. Thanks.